DeFi has a UX problem. There are many interesting investment opportunities, but often it's quite hard to identify the ones that would fit our investment profile. I made other videos on this channel showing how we can use AI automation to streamline the do-your-own-research phase. In this video, I want to show you something a bit different. I built a proof-of-concept AI agent that takes an Ethereum wallet and input and assigns it a risk score based on on-chain data. The score goes from 0 to 100 and represents how much appetite for risk this DeFi user has. Basically, do they play it safe or are they a complete degen? Hi, for those that don't know me, I'm Renato Budnic, PhD in Applied Mathematics and Blockchain Intelligence Engineer. I'm going to show you how I used langgraph to build an AI agent that autonomously gathers data and uses it to compute financial risk metrics. The use case for this could be either self-evaluating your own DeFi positions or understanding where other investors fall on the risk-rewards curve. Here you can see the basic Next.js frontend I made, displaying the risk score for Vitalik's vitalik.eth address. To be honest, I'm not sure how accurate this is, but I suspect not too much. In fact, if you go see in the logs, the problem is that no price was found for some tokens, and thus they count as zero value and they are very low on this metric. But before getting into the specifics, remember that this is only a proof of concept and not production ready. From my point of view, the real interest here lies in the inner workings and not so much in the end result. But do let me know in the comments what you think about this score for vitalik.eth. So how does it work? Well, here on GitHub you can find a lot of information about it, and right at the end there is this link to this other markdown file. And this is actually where I started. I tried to figure out what metrics could help me quantify the risk appetite of a DeFi investor. And with the help of AI, I came up with this extensive list of metrics. So for example, the loan to value of the wallet or the portfolio churn rate of the wallet. Okay, all sorts of metrics that mostly can be computed from on-chain data. The hypothesis here is that if you had all of these metrics for a given wallet and you would give this to a human analyst, well, they would have more than enough data to give you an accurate risk assessment, right? A score from 0 to 100. So then the main idea would be, okay, let's try to compute as many of those as possible and then make one prompt to the LLM saying like, you are an expert DeFi analyst, okay? We have all this data about this wallet, all these metrics, give a risk assessment. But then where does the agentic loop come in? Well, we first need to gather the data, and you can see it has these tools available. So there are three types of tools: API tools, metric tools, and utility tools. So at each loop, a call to an LLM is made, passing it a list of the previous message and the available tools. And here you can find the main prompt being used. So it's saying like, you're an expert DeFi analyst. There are three types of tools at your disposal. API, these will fetch raw data. Metric star, these are pure functions that compute a variety of different metrics. Okay, they're the ones we were looking at before, and some helpful utilities. I guess this is a typo. I forgot to take it out. So basically there are two main nodes in the langgraph agent. One is the LLM node that is given this choice of available tools and that prompt. And then there's a node for the tools, which executes the tools as they are called by the LLM. This isn't really a node. We create a memory, okay, for the LLM of containing the previous end messages. At the very end, there is the final prompt asking the LLM to assign the score. And you can find that prompt here. Okay, so you are an expert DeFi analyst. Your task is to assign a score. Here there will be all the metrics that were computed, and your task is to give it to give a score from 0 to 100 alongside the justification of why the score was chosen. Like this, I mimic the process that I usually follow at work when conducting a due diligence. Separate that data collection part, which should be an impartial summary of the facts, from the final assessment, which should be a subjective expert's opinion grounded in data. So let's get into the tools then. This is the code base. Here inside providers, there will be for each API endpoint, there will be a function. There we have to put the tool decorator from LangChain, and we can add this decorator that I made to basically automatically rate limit the endpoint. Okay, so not allow the LLM to call it, in this case, more than twice every 10 seconds. And here, yeah, I have some API endpoints for Alchemy, okay, to get the portfolio, and the transaction history for CoinGecko to get contract data, coin data, and some other stuff. Of course, you could also have here, just as well, you could have connections to node indexers, okay, to get actual on-chain data. I was trying, of course, here to simplify and to make a fast working prototype. Then here we have the metrics, okay, and there is a base class for the metrics that inherits from the Pydantic base model. The metric should have a name, a description, a value, okay, and this will be set individually by each subclass of this metric output, and as well as an explanation, okay, for the value. By the way, I implemented only these 5 metrics out of all the ones we were looking at earlier, right? The ones generated with AI. And so basically for each metric, we have a function, right, that computes that. It's also decorated with the tool decorator from LangChain. But if you see the interesting part, at least that I find, is that both the input and the output are very well specified with a Pydantic class. So if we look at, for example, this expected output, okay, it inherits from the base metric output we saw earlier. Here there's actually an additional field, percentage exposure. This is specific to this metric, okay, exotic asset exposure. This will be given in percentage, but we want to have this common value method such that we have a common interface from the outside, right, to call this class like if it were a black box and just get the value of the metric. And in this case, it will return this value. Even the inputs, right, are specified very well. So in this case, it's a list of assets, which so it's a list of items, each with a symbol, a USD value, and a market cap rank. So that the fact that we are specifying the input so well means that when we give this tool to the LLM knows exactly what quantities it needs in order to call this function, right? So it can query the API endpoints until it has the data and then prepare a call for this metric, passing on that data. Right? And finally, there are some utilities for the agent, okay, like if you get in an error loop, call this to stop and do some simple maths in order to not have the LLM do math by itself, right? So what I like about this architecture is that by having the tools separated like this between API and metric, it is a very modular architecture, right? I could add a new API endpoint or a new metric completely independently one of the other, right? There is no glue needed because I specified for the metric. So I specified for the metric the inputs, that's true, but I didn't glue them, let's say. I didn't write any code to glue them to the outputs of the API. That's kind of actually the whole point of this architecture. Like I'm trying to use the LLM to do this mapping of data. And that's why in theory with this architecture, you could just return, you could just dump the whole, whatever the API endpoint returns, you could just dump it. So here in the comment above, you see this is an example of what this endpoint returns. And I could, of course, and that's what I was doing in the beginning, you know, like parse it and prepare a nice structured JSON and return that. But, you know, as long as context size is not a problem, and well, in practice, spoiler alert, it actually is, but let's say in theory, okay, with this architecture, I could just not care about whatever the upstream endpoint is returning and just dump the JSON, which makes it very convenient because I don't have to maintain code like, okay, like this code would be that needs to be aware of the specific schema coming from the API endpoint. It has to be updated right when they change the schema and so on. So the code, as you can see, it's all in Python. It's using langgraph for the agent. Okay, so we have an agent state, and then we have an LLM node, as I was mentioning, that takes the state as input, does stuff to the state, okay, and passes on to the next node. And for the very final prompt, okay, I have a special node for that, and I'm actually using the instructor library, which is a library that I really love because it does something simple, but it does it really well, and that is to simply give a prompt right to the LLM and give it a Pydantic model and ensure that whatever we receive out of the LLM will be actually an instance of this Pydantic model. Okay, so it has some retry logic and stuff. To actually run the code, there are two possibilities. For testing, I used a lot the CLI interface that I did with Click, and you can specify a lot of logging options. It's even using the checkpoint feature from langgraph, which is basically checkpointing each run and storing it in a SQLite database. And then there's an option to resume a run from a saved checkpoint. And then there is the other way to interact with it is with a frontend. Okay, so there is this fastapi interface to the agent code. Okay, and then it has this SSE endpoint to communicate in real time the status updates as the agent is running to the front end. And then, of course, the frontend itself, which is a very simple one-page Next.js app with Tailwind CSS. Okay, so let's try to run it with another address associated with Vitalik. Let's see how it goes. And you see, it tells you, okay, the LLM first tool it's going to use was the portfolio, okay, from Alchemy. And now sometimes the LLM, it will return the tools to call, but it will also give you some reasoning, okay, as to what it's done and what it's going to do. And if you open here the logs, you can see the full reasoning. In this case, okay, for this wallet, it gave a very high score. As I said, these results are not very attendable, but you see the interesting part is that at the last result, the very last thing it returns is a structured JSON. This is thanks to an instructor, like we get a risk score field, a justification, which is then what is being displayed here, and the metrics, okay, for each. This, again, remember, was the basic metric output interface, okay, that all metrics subclass from. So they all have a metric name, a description of the metric, the value, and the explanation for the value. And then if you go up, okay, you can kind of get a better feel for why it gave the score, because as usual, it's probably not very accurate, and it's probably due to missing data. Maybe there are some tokens that it cannot find on CoinGecko, it cannot find prices for. For example, you see for this, there was no market cap rank available, whereas to compute the exotic asset exposure, you kind of need that. So then you could go into the logs to see how did it actually call this function that requires a market cap. Did it put it to 0? Did it put it to a very high number? Yeah, here you see I tried to call the utility math multiplication, but then it says it seems there was an error with converting the token balances to a float for the multiplication operation. And you can see the logs, by the way, of the Docker stack like this. So here you can see a bit more accurate logs. And for example, you see this multiplication failed. Well, because it's trying to call it, okay, yes, this is actually a floating point number. This is not. But yeah, you can see where this is going. I think the architecture has some really interesting modularity in it. In fact, because of that, I would say that the main loop works very well. The LLM is able to figure out which data provider it should call to compute the metrics it needs. However, so A, there's a limited number of metrics that the LLM tries to compute, and B, we don't, from many runs, looking at many logs of this, I can say it rarely finds all the data it requires. But the core architecture, I think, is solid. And of course, one of the first things to improve would be to enrich the API endpoints, maybe to curate them better also, right? I was saying, yeah, you can just dump the whole JSON. For sure, you can do that, but it would be better if we had a complete mapping. If we had something like an NCP server, right, for these APIs, it would be even better, because then you could basically give access to the full API with minimal integration code, right? You could give access to the agent to the full API, not just to selected endpoints. And then, yeah, there's also the context window size problem, right? Right now I have a fail-safe logic, okay, that checks the token size of each message before giving it to the LLM, and it truncates if it's too long. Of course, that could be done better, especially by curating more the API endpoints or summarizing better the messages before passing them on. So to conclude, this was my first time doing an actual AI agent, okay, where the LLM is part of a main loop and is asked to decide what to do next. I learned a lot from this project. The first thing will be that debugging this in general is very challenging and can get quite involved, because you have to backtrack the decisions that were made by the AI to see where it kind of went wrong. And in order to do that, structured logs are very important. So I actually spent quite some time on like perfecting the logs just to make them more readable and to understand better what was going on. Also, as I mentioned, you always want to keep in mind the size of the context window. And at first I kind of ignored this, but then I actually went back and implemented the checks with tick token to look at the size of each message, even each API endpoint, the JSON it gives back, like computing the token size, just to get an idea of like how much are we filling the context window and how much are we truncating and so on. But what I love about this is that I see a lot of potential for it. I think the architecture is quite flexible and could be used for many other problems, where you basically have a data collection phase and then a subjective assessment phase at the end. So I hope you found at least some of this useful, and please, if yes, please give a sign of life, click like, leave a comment, subscribe, so I know that I'm not just sending these out in the void. I would be so excited to get my first comment, so yeah, you could be the first one. Bye, see you next time.